Okay, so previously we've been talking about variational integrators from the Lagrangian perspective. So let me now briefly talk about how one might construct variational integrators purely from the Hamiltonian perspective, and then more importantly, why this is an issue which is worth studying. Right. So this is the motivation, if you will, for studying Hamiltonian variational integrators. So you probably know that when you have a Lagrangian or Hamiltonian which is regular, which is to say that the Legendre transform is invertible, then there's this one-to-one correspondence between Lagrangian and Hamiltonian mechanics. Okay, so if you have a Hamiltonian which depends on position and momentum, and you have Lagrangian which depends on position and velocity, then these things are related by the Legendre transforms. So in this direction, it's given by the Legendre transform generated by the Hamiltonian, and in this direction, it's the Legendre transform generated by the Lagrangian. Okay. All right. And the problem, of course, is what happens if the Lagrangian Hamiltonian is not hyperregular, which is to say that one of these maps is not invertible. Okay, so that's what we have in mind. In particular, if you start off with the Hamiltonian side and you have a Hamiltonian which is not regular, then you won't be able to go to the Lagrangian side, where we have developed methods for constructing discrete Lagrangians, LD, Q0, Q1. Okay. Then if you have a discrete Lagrangian, it's like, as you might expect, it's like there is going to be a way to get from a discrete Lagrangian to what we call a discrete Hamiltonian, which is also a generating function of the symplectic map, but it's a different type of generating function, which is to say that the generating function doesn't depend on initial position and final position, but initial position and final momentum as one possibility, and then there's another version which we call HD minus, which is initial momentum and final position. Okay, so and this is related by FLD. Okay, and the idea, if you will, is that we would like to ask the question whether it's possible to go from a Hamiltonian to one of these discrete Hamiltonians directly instead of going via this diagram, if you will. And as I said before, it's like the problem with trying to go via the Lagrangian route is that there are examples where the Hamiltonian is non-degenerate, where the Hamiltonian is degenerate, and then there's no Lagrangian analog. So let me sort of just give you an example of such a degenerate Hamiltonian. It's a simple, maybe somewhat contrived example, but nevertheless it will illustrate some of the challenges one has. It's like, so this is an example of a degenerate Hamiltonian. And in particular, it has the form HQP is equal to just Q times P, if you will, right? And then your Legendre transform, okay, FH, which is a map from T star Q to TQ, okay, which is given the following way. It maps Q and P, position and momentum, into position and the partial of the Hamiltonian in respect to the momentum variable. Okay, and then if you recall, if you had Hamiltonian, which was one of these simple mechanical systems which had a quadratic Hamiltonian, a quadratic kinetic energy term, which looks like, say, 1/2 P transpose M inverse P, right? So a common form of a Hamiltonian might be HQP is 1/2 P transpose M inverse P plus the potential V, which depends on Q, right? So that's the Hamiltonian associated with the Lagrangian, which looks like 1/2 Q dot transpose M Q dot minus V of Q. All right. So if you had that particular Hamiltonian, then this sort of Legendre transform generated by the Hamiltonian would give you Q comma M inverse P, which in the usual case here, right, would just correspond to Q and Q dot, right, because this will be M inverse times P, and P is just M Q dot. Okay, so this is the usual kind of Legendre transform. It's like which does the things you expect. But let's see what happens if you have a Legendre transform like this, but with this particular Hamiltonian, which is just position times momentum. Okay, so so that in this case, right, in the case where H equals to QP, if you prefer, it's like I could do something like Q transpose P, right? Then this thing just becomes Q and Q. So basically what is happening is that the Legendre transform you have here loses all information about the momentum, and so clearly that's not invertible. Okay, so the Legendre transform is not invertible. This is an example of a Hamiltonian which is degenerate, which is to say that the Legendre transform is not invertible. Okay, so even if that's the case, let's see if we can do something about the Lagrangian. Okay, so usually you write the Hamiltonians and Lagrangians. It's like by writing down some sort of Legendre transform and restricting to the image of the Legendre transform. So what I mean by that is that normally you write something in this case as P Q dot minus H QP, right? Something to that effect. Or if you were writing Hamiltonian in terms of Lagrangian, you would have the Hamiltonian as PQ dot minus LQ dot. Okay, but the bottom line, if you will, is that if you look at the left and right hand sides, right, on the left hand side you only have Q and Q dot. On the right hand side there's also a P involved, right? So what you normally would do is that you restrict yourself to the image of the Legendre transform, which is say that I restrict myself to the condition that P is equal to dH dP, right? Sorry, Q dot is equal to dH dP. I'm sorry, that's what I meant. All right, so Q dot is equal to dH dP, and then you use this relationship to solve for P in terms of Q dot. Okay, so that's normally what would happen. You can't do this here because the Legendre transform is not invertible, and you basically have to invert this in order to solve for P in terms of Q. P in terms of Q and Q dot. Okay, so that's a problem. Okay, but what you can also show is that this is of course equal to the extremizer of PQ dot minus H QP over the unknown variable, which is P. Okay, so that's something that's like we could actually compute for this degenerate Hamiltonian. So let's see what happens. Okay, so that's equal to the extremizer of P Q dot minus H, which is let's say Q and P. All right, and I extremize over P. Then it's easy to convince yourself that the extremizer of this occurs when Q dot is equal to Q. Okay, so but when Q dot is equal to Q, then this thing is identically 0. Okay, so the Lagrangian, which is associated with this degenerate Hamiltonian, is identically 0. Okay, so clearly you have a problem here that the Lagrangian really doesn't encode anything about the Hamiltonian dynamics associated with this discrete Hamiltonian. So that's part of the problem. But that's another problem. Okay, so so here it's like in this picture, I've sort of taken care to say that the generating functions I want to use to construct the discrete Hamiltonian flow here is what's called a type 1 generating function, which depends on initial and final position. And then this is a different type of generating function, which depends on the initial position and final momentum. Okay, so now let me try to explain why it is that we want to frame it in terms of one of these other types of generating functions instead. Okay, so again, it's like motivated by this degenerate Hamiltonian. Okay, so what I'm going to do is I'm going to write down the boundary conditions, if you will. Sorry, let me rephrase it. I'll first write down Hamilton's equations associated with this, and then I'll ask it's like what kind of boundary conditions we can impose. It's like on this, right? So Hamilton's equations for that particular Hamiltonian is given by just Q dot is equal to dH dP, right, which is Q, right, and then P dot is equal to minus dH dQ, okay, which is minus P. Okay, so that's Hamilton's equations. And of course, there's an exact solution associated with this. This is not so difficult because they just decompose, right? I mean, it's like, yeah, so they're just sort of fully, it's like sort of independent of each other. So you get the solution is that Q of t is Q at initial time times the exponential in time, and then P of t is P at the initial time times the exponential minus t. Okay, so that's the exact solution. Okay, so so when we discussed discrete Lagrangians, you recall that the way you do this is that you specify the initial position and the final position, and at the back of your mind you should also think that you specify the time step as well. So to construct your discrete Lagrangian, right, you pick sort of the initial position, the final position, and the time step h. Okay, so the problem, if you will, it's like with then this kind of type 1 generating function is that when you look at the exact solution of this degenerate Hamiltonian, right, you don't have the flexibility to pick all three of these things simultaneously, right? So you can pick the initial position, which would be Q0, that's fine. You can pick the time, that's okay as well. But if you do that, then you are prescribed, it's like, as to what the position at the final time is, right? So if you pick the initial position and the time, then you have chosen what Q1 is in some sense. So you don't have that freedom, okay? To construct the discrete Hamiltonian, okay, which I called HD plus, right? What I did was that I pick an initial position, Q0, I pick a final momentum, P1, and I pick a time h. So now, if you look again at the exact solution associated with this degenerate Hamiltonian, then everything is fine, right? So if I pick the initial position and I pick the time, I get the final position as a consequence of that. That is unconstrained, right? Nowhere have I prescribed it. If I pick the final momentum and the time, I get the initial momentum. That's again unconstrained. So I have the flexibility to choose Q0, P1, and H in a way which is compatible with exact solutions of this degenerate Hamiltonian, but I don't have the flexibility in general of choosing Q0, Q1, and H arbitrarily for this particular system of equations. Okay, so again, what that sort of alludes to is the following, that when you want to construct a variational integrator for a degenerate Hamiltonian system, then on the one hand, you can't rely on just going to the Lagrangian side and then using the usual Lagrangian construction and then sort of pulling that back to the Hamiltonian side. Okay, what you really want to do is you want to start on the Hamiltonian side because they may not be a Lagrangian side when the Hamiltonian is degenerate. Okay, and then what you want to do with that Hamiltonian is you would like to construct a generating function which is not just a type 1 generating function, but one of these what are called type 2 and type 3 generating functions, where you either pick the initial position and final momentum, or you pick the initial momentum and the final position. Okay, so that sort of at least motivates why it is that we're going to develop, it's like our theory of Hamiltonian variational integrators in terms of expressing the thing in terms of what are called discrete Hamiltonians, which are going to be type 2 or type 3 generating functions, and they're going to just involve the Hamiltonian, and they will not resort, it's like, to going to the Lagrangian side. Okay, so that's the motivation for doing this.